it. So it depends on the tumor tissue characteristics, not only the cells.
Thank you.
Any more questions from audience? So thank you, sir. Sir has given a wonderful and knowledgeable talk on cancer thermal therapy. Sir has explained the reasons of cancers. He has also explained the techniques of treatment of cancers. He told about the role of nanoparticles for treatment of cancers. So thank you, sir, for taking the time for us.
Okay, thanks.
I am hand over the proceeding to Miss Asha Kumari. Dr. Asha.
Thank you, Dr. Indu. Am I audible?
Yeah, Dr. Indu, may I leave now?
Yeah. Yes,
okay.
Okay, good morning to one and all present here.
Asha, continue, Asha, continue.
Okay, ma'am. Good morning to one and all present here. Now we are going to start session 12 of this international workshop. I would like to welcome Dr. Dinesh Pathak, who is expert speaker for this session. Before starting this session, I would like to introduce our speaker to audience. Dr. Pathak has done his PhD from GNU, Amritsar. He completed his postdoc from University of Wadowice, Czech Republic, Europe. Dr. Pathak was visiting scientist from 2012 to 2015 in Photovoltaic Laboratory, Queen's University, Canada. He has published more than 60 research papers with 476 citations. In addition to this, he is a reviewer of 60 plus journals. Presently, Dr. Pathak is working as head of physics department, Sri Sai University, Palampur, Himachal Pradesh. His area of research is nanostructures, compounds, semiconductors, oxide nanocomposites, ion beam synthesis of nanomaterials, organic semiconductors, and inorganic hybrid semiconductors. Now I request Dr. Dinesh Pathak to start his talk. Please, sir.
Hello, good morning. Good morning to all.
Good morning.
Is my PPT visible on the screen?
Sir, your presentation is not visible. Yes, sir. Now it's visible, sir.
Okay. No. Okay, is it visible now?
Yes, sir, it is visible.
Okay, good morning to all. I'm Dinesh Pathak, as already introduced by the host. So, I will be presenting today preliminary work of based upon nanofibers, which we just started from last 1 year. We understand that this 21st century, especially 2020, was a very difficult year for the mankind because of the novel coronavirus. And now we are in the stage of vaccination, and but for 1 year has already passed, and 1 year has already passed, and we were forced to live in isolation, and the whole world was in the influence, and we were forced to have masks on our face for the entire year, and we're still afraid that the situation may still go further for some time till the vaccination. So people are also looking, along with vaccination, people are also looking worldwide for protective masks, and the nanofiber based masks are already in the market. Even in India, there is a company, the mask name is Swasa. You can buy a nanofiber based mask in 100 rupees. So we also started, considering this work, we also started to have the control of the porosity and structural control based upon nanotechnology, the field, especially nanofibers, so that we can have research, a bit preliminary research on this. So actually this field comes in the domain of this membrane filtration. We understand that from very old civilization time, the filtration was very necessary. Even in the older time, people were filtering water to get the pure water. And with the increase in population, this challenge is going more and more because of so much pollution. So membrane filtration, the field of nanofiber, it comes in the domain of membrane filtration, where we need to filter a water to provide pure water to the in the cities and in other places as well. And also sometimes we need to filter air. Sometimes we need to protect ourselves from the various viruses. Sometimes we need the medical dressing, smart medical dressing, where the water cannot, where the water should not penetrate till to the wounds. And also in many other optoelectronic industries, like in batteries, we need battery separator. So this field, this can be achieved by having smart nanofibers. Smart nanofibers means controlling the porosity and diameter of the nanofibers according to our desire. So nanofiber is not nanofiber market. Nanofiber research is not a new. It has not started from last year, but the market is already reached US dollar, around 500 million US dollar market is there. I was working in a nanofiber industry after my postdoc in Czech Republic for few months, and even in Czech Republic is a very small country. Even in Czech Republic, there were around 50 nanofiber industries. So, considering this work along with my one of the MPhil student, we started this work last year, and I made this presentation as a preliminary presentation of our work, where the new researchers, they can understand that what are nanofiber, how they can be produced. So nanofibers, from this PPT, we can see that nanofiber are the structure, fiber-like structure, where we have fibers, and in between we have some porous voids. So these porous voids can be, or these porosity can be controlled by, when we make nanofiber, we can control the porosity. Either we can make them maybe 10 nanometer, or 20 nanometer, or 25 nanometer, and similarly by controlling the diameter and other experimental conditions. So, for example, if we wish to stop the coronavirus, so we should have porosity of the size more than the coronavirus here. So similarly, if we wish to filter water, water has many toxic elements if it is polluted. So we can control the porosity for that application. So if we wish to say have, if we wish to stop the water, even for example, in some application we need to stop the virus and bacteria. So we can control we can have that desired porosity according to the bigger, lesser than the size of the water. So we can make air filter mask, virus filter mask, or water filter. We can use the nanofibers for water filtration in batteries as battery separator. So there are plenty of applications of nanofibers. So in general, we define nanofiber. They have fiber-like structure. Even if you see cotton by naked eye, you see there are some fiber, but they are not, obviously they are not nano. But if you see a material where if you have produced nanofibers, if you see that material with the help of very high resolution microscope, which are either scanning electron microscope or high resolution transmission electron microscope, so you can see such image. So we define them nanofibers when the diameter of the fiber is up to from 1 to 100 nanometer, and porosity is in between. Porosity is according to our desire. So further, there are many applications for wound dressing, for in other medical purposes, like PPE kits are very much in demand nowadays. So there we can sandwich in those PPE kits, we can sandwich the nanofiber so that we can protect the human body from the viruses. Similarly, in cosmetic industry, in other filtration, water filtration, air filtration, or optoelectronic application, we have so many plenty of applications. So considering this, even if there are even application of nanofiber in aeroplane industry, where we can prevent the sounds to reach to the passengers sitting inside. So we can protect, we can have so plenty of applications. So why nanofibers? There are other mediums as well, like you have RO system at your home, or for filtration you can use other things as well. But why nanofiber? Because their size is very easily tunable. We can just control the conditions when we are growing nanofibers, and we can control the porosity and diameter, and then we can have plenty of applications. Also, they are very lightweight. Obviously, if we will have a thin layer of nanofiber sandwich in some media, they will be lightweight. And so, considering these, people are moving toward the nanofiber nanotechnology solutions for these. And then, how nanofibers can be made out? They can be either of polymers, or they can be a blend of polymer and some metal oxides. And later, if we sinter, those polymers can be ejected out, and we can have. So why we make a blend? Because to have some mechanical strength of those obtained nanofibers. So these are just points that of which materials we can make nanofiber, either pure polymers or polymer inorganic blends. Then this slide is just showing about the properties of nanofibers. They have very large surface to volume ratio. Tunable porosity. Tunable porosity means if we desire to stop novel coronavirus, then we should have porosity. It is expected that the size of coronavirus is around 110 nanometer. So similarly, other bacteria, they have size in micro, so they can also be stopped. If we wish to filter water, so that may have that type of nanofiber, which should have different porosity. So every application requires a different porosity. So they can the porosity can be tuned. The porosity can be tuned by controlling the experimental condition which we do during the fabrication of nanofiber. They are lightweight, structural control is easy, and they have low cost as well. So that is these properties attract researchers toward nanofibers. So how nanofiber can be? Am I audible? If someone can confirm.
Yes, sir.
Yes, sir.
Okay. Because I am not seeing the people here, only my slides. So there are many methods to fabricate nanofiber in laboratory as well as in industry. You can have electrospinning, then you can have template synthesis, then force spinning. Force spinning is a kind of instrument where we have a big chamber and you fill the solution inside, and there are nanopores, in hundreds of nanopores in the outer region, and when you rotate it with very heavy speed, then then the nano material comes out, and that can be dried or sintered later depending upon the application. So there are many methods like this. And now coming to, we actually used electrospinning. Actually, one of my colleagues, Dr. Aman Mahajan, he is having this machine at Department of Physics, Guru Nanak Dev University, Amritsar. And I also worked, actually this experimental work which I am presenting here, this was carried out one of my MPhil student who just submitted his thesis. But when I was in Czech Republic in industry, I was working on electrospinning method as well as force spinning. Then we can have melt spinning even. We can just melt a material and then we can make nanofiber. That type kind of instrument is different. But we used electrospinning. So what is electrospinning? I will come to the instrument. This is the instrument actually. eSpin, this company is actually Indian. One of the fellows, Mr. Dr. Sandeep Patil, he was a fellow at IIT Kanpur, and he established this company. And this machine, my colleague Dr. Aman Mahajan, he purchased from this. He purchased. So what is electrospinning? We should make first a solution, either a polymer solution or a blend of polymer and metal oxide precursor. So we must have some question that why I'm saying that we are adding metal oxide in polymer, because polymers they don't have much good strength. So sometimes that is why we are using metal oxide nanofibers. And later, if we wish to have blended nanofiber, that they can be used as they are. And if we wish to remove the polymer, so that can be calcinated. Calcination is a phenomena when we heat the final product at high temperature to remove the extra precursors, and then we can have titanium oxide nanofiber or other metal oxide nanofiber. So what we do here is we just make, if this electrospinning, actually the instrument varies from company to company. So this is syringe based electrospinning method. The earlier equipment on which I was working in Czech Republic for some time, there we were having a chamber and we were filling the solution. So, but the principle is same. So what is the principle? Just we fill the either syringe or a chamber with the solution, and we apply opposite potentials over. This is actually drum here, collector, this one, and we have syringe here. So we apply opposite potential, either positive here, maybe, or negative here. So because of the high potential, the solution is forced from here to make fiber-like structure over this drum. So this is the principle of actually electrospinning method. And again, this slide is repeated again about the applications. So we use titanium oxide because it is very versatile, low cost. It has applications. Because along with the filtration, we can use nanofiber in other applications as well, either protective coating, self-cleaning windows, or in solar cell, water treatment, etc. So that is why titanium oxide was blended with this polymer PVP. And this is actually precursor of titanium oxide. One solution we made of it, and second PVP. Then both solutions were mixed together, and then this is just a preliminary experiment which we did, that we varied the percentage of concentration of polymer to have to obtain different porosity and different diameter. So just a simple experiment. We mixed two solutions, and then just again, but these parameter we fixed here, and then this is actually the close view of the experiment. That this is a syringe. So because this is syringe-based electrospinning equipment, so we filled the solution over here, and we applied potential, one-sided potential here, one over the drum, and then fiber-like structure that is forced by electric field to have layers over here, and they can be collected later. If we wish to have the blended nanofiber of the material which we started with, we will not heat in later. And if we wish to remove the polymer to have only titanium oxide fiber, they can be calcinated. So then what we did is we obtained the nanofiber material, and then to see obviously all material scientists, they understand that the characterizations are very necessary. What we have produced and what is the internal structure to see possible application further. So we did some of the three different nanofiber samples obtained. So you can see here that we were successful in obtaining nanofibers. These are the fibers, and the voids, we name them as porous, if they are porous, and so porosity is optimized here. Here we have different porosity, here different, and here is different. So again, various samples can be optimized, various conditions can be further optimized. We can control the parameter further, means we can change the potential, then porosity will be different. Obviously, we can change the distance, even this. We can change the polymer concentration as well. So the porosity can be optimized, and further now you will see that what we did, why we did this, because again initially I said that because they are porous, highly porous materials, so they can be used as membrane for either water filtration or air filtration or protection from various masks. What we are using is during this COVID time, we have masks of simple either cotton or other materials. But if we will sandwich these layers in between the two cloths, or maybe some different things, then obviously if the size, if the porosity of porosity is maybe is less than, maybe if the porosity is maybe say 80 nanometer or 70 nanometer, obviously the coronavirus that will not pass through it, because some still research is going on that if this novel coronavirus COVID-19, it sustain in air, how much it travel in air. So, and that is why the government and WHO has warned us that we should maintain some distance. But if we will have masks like this of porosity less than 100 nanometer, air, we can easily breathe. We can easily breathe, but the various viruses and bacteria, they will not pass through. Similarly, if we optimize the porosity for the size, the porous size is optimized for water. We can filter water. We can have so many other applications. So here we see that we successfully obtained. This is not a new research. The mask is already in market, and even if you buy, I don't know if they are available in Himachal or not. But if you go to a medical shop, you can ask for a nanofiber mask. The cost is only around 100 rupees, which initially this is Swasa company they launched. Swasa company was established by is the same guy who established this E-spin company for nanofiber. We just started work that for the further possibility of controlling the porosity by optimizing the various conditions, either solution concentration and all these things, to see the possibility of these and further, which we will do for other applications as well. So this is just a data obtained from SAM that we found that porosity is of the order of this range. XRD just suggested that they were amorphous, but we were not bothered about the XRD results because we are not interested. When we are using nanofibers for masks, we are not interested in XRD, that we don't bother which kind of structure they have. But when we are going for some optoelectronic application, obviously we need to see the structure. So that is why XRD was also performed, but we found that they were amorphous. BET analysis is a technique that, because by SEM, the exact idea of porosity cannot be estimated. SEM is not accurate for porosity. So what we do is, BET is a method where we use adsorption and desorption of non-reacting gases. This technique is available at IIT Mandi. So if someone is interested, maybe many of you are maybe doing. So what we do is we have material inside the chamber, and it is exposed to the non-reactive gases, and then adsorption and desorption that estimate how much porous they are. So we found that the porosity is around 4 nanometer, 2 nanometer, and 1.5 or something around, again 2 nanometer, which is very good for maybe various applications, like especially stopping the virus, because virus has bigger size. Coronavirus is not new. If you are aware, the novel coronavirus, which has a new structure, which came from Wuhan, as people are saying, this has a new structure. But if you see in the internet, if you're a researcher, a beginning researcher, then if you search on the internet, there are many papers published from around 2008 to till date on coronavirus. So, but even we are not still aware. People are saying, WHO is saying that the coronavirus has size around 120 nanometer, and other viruses has a bigger size than this, like Ebola and etc. And so many other viruses. So obviously, with this porosity, they will not pass through these fibers, but air can pass through. So we can breathe, and we will be protected from these viruses. So similarly, various other this is again just repetition. We also tried to filter water, but experiment was not a good big success. So we will in the process to do this again with some other colleagues. So we will see if we will be able to. Obviously, from here it is seen that we got some filtration done, but actually we could not filter arsenic and lead with the help of these membranes or fibers, but we are still in the process to do and repeat the experiments. So this slide is again a comparison that if we obtain a porous material which has porosity of 1 to 4 nanometer, what can be the applications? Because size of water molecule is less than this, so that will cross through it. Water can go inside that, but the heavy elements, they have bigger size, they will not pass through it. The viruses are generally like Ebola, they are well studied. The Ebola virus, we know that the outbreak was last year, or maybe 4 to 5 years before in African countries. So that has size less than 100 nanometer, but more than 50 nanometer, so that they can be stopped with these fibers. Then SARS and other bird flu like Zika or Hanta virus, which just came out in China from BCB, and we found a few months before. So they can be protected with the help of these nanofibers. Just the thing is that just means they can have many applications controlling either COVID or these Hanta or maybe SARS or maybe some other things. Just the thing is to control the porosity. And as a material scientist, we obviously are able to control the porosity just by having optimized experimental conditions, changing the pH of the polymer, changing the in electrospinning, changing the potential, changing the distance of that syringe and the collecting drum, or many other conditions. We can change the porosity, and obviously the different porous materials, these beautiful materials, they can have many applications in filtration or battery separators or in other smart material in future. So what are the challenges actually when we are using a fiber material, nanofiber material for some application in optoelectronic, not in optoelectronic, but if we are in filtration or somewhere there. Can you please confirm if you are able to listen to me?
Yes, sir. Yes, sir.
Yes, sir. Yes, sir.
So means there are many challenges still in the field of nanofibers to control.
Sorry, sir, you are not audible.
Actually, I got a call in between. I'm still audible?
Yes, sir, you are
Yes, sir.
audible.
Yes, sir. Yes, sir.
Coming to conclusion, that there are still many challenges which scientists, various scientists and various researchers need to address. So if you have some question, we can discuss. And if someone from you, from those who are in master degree or somewhere, if they wish to join research in this field, they can call me or they can contact me on this mail ID, and we can continue further. Thank you. Thank you once again.
Okay, thank you, sir. Now session is open for queries. Is there any query for participants?
If you have some question, or if not, then maybe you can mail me also. Also later, I have given my mail ID there.
Is there any query for from participants? Okay, I think there is no query. Okay, sir. Thank you, Dr. Pathak.
Thank
Dr.
you.
Pathak, Dr. Pathak has, yes. Yes,
Yeah, if
please.
still later you will have, maybe some participant will have some question, or maybe some suggestion, or maybe if some people wish to join research in this field, then we can collaborate, and I welcome the people. Means if someone have some query, even they can mail me, please. Thank you.
Okay, sir. Thank you. Thank you very much, sir. Thank you, Dr. Pathak. Dr. Pathak has wonderfully explained about nanofibers. He has also explained how we can synthesize nanofibers, what are various applications of nanofibers, and he has also explained about use of these nanofibers for against COVID-19. And he has also explained about different porosity assessment techniques. Thank you, Dr. Pathak. Now, I declare the end of this session for today's workshop. There will be, now we will meet on tomorrow. Tomorrow there will be only one session at 10 a.m. So I hope all the participants will join us for tomorrow on 10 a.m. Thank you all.
It was very informative.
Thank you.